So all, let's start with our today's DSA journey with this amazing visualizer by dsa.chaicode.com. Use this link to get a 7-day free trial. Let's go to our question. So previously we completed this question sliding window maximum and the sliding window is completed. Now let's move to stack. So stack is a data structure. A stack is a simple container with personality. You may only touch the top and add with push, remove with pop. The first thing to out, the last thing in is the first thing to out. Okay. So take this example. So we have this stack. Okay. In a stack, we only touch the value which stored in the top of the stack. Okay, 3729. Let's take 3729. So this is four elements or numbers. So if we take this 3 at the first and if you want to insert it into the stack, in stack we call the insert as push. So we have to push this element. So just push this element. Okay. So every time we have to want to take some element out of the stack, we also always we can we can take the element from the top. So we can only touch these three. We can only touch these three. Even we want to pop, we have to pop from the top. So let's suppose we insert 3. Then when we come and insert 2, we insert 2 on the top of 3. We insert 2 on the top of 3. And when we want to remove element, when you want to remove an element, we cannot remove 3 at the starting. Okay, first we have to remove this 2 which is actually a topmost. So it is something like plates, all the plates stored one by one, and when you take you are into a function and all the plate stored from the top to bottom, most of them actually when you ask for a plate they give the top one. Similarly here, so in any time when you want to get one element, the first thing you will get are 2, not the 3, are 2. When you want to poop an element uh, or remove the element from the stack, we call it here as pop. So we have to remove this 2, not 3. First we have to remove this 2. Now in the top there are only 3, so 3. So when you want to push, we have to push it here, push, and now again push. So which is the first element inserted? The 3. Which is the second element inserted? 2. Which is the third element inserted? 7. Which is the last element to insert? 9. And now when you want to remove the element or pop the element from the stack, what which element should we take at the first? First take 9, remove 9. Take 7, remove 7. Take 2, remove 2. Take 3, remove 3. If any style you push, this element, any style you push this element, you can only push from one side on, and on the same side you have to pop. So the last element which comes here is 3, which you push in this stack is 3. And when you want to remove the element or pop the element, that will also be 3. So for that reason, stack is called leaf O. Nothing but last in, fast out. Last in, fast out. Last in, the last element which you insert is 3 and the first element which you out is 3. Okay. For this reason, the stack is called last in, fast out. So let's check our first question. Okay. 5 times. I don't know. Okay, let's do with another window. So this is our stack. Let me check and come back to you. Okay, so now the website is working. Let's visualize stack again. So we can push 3, then push 7, then push 2, then we have pop. We push 9, we have to pop. We have to pop that from the top. Pop from the top, pop from the top. This is the question. Let's come to our question, which is valid parenthesis. So given a string of brackets containing character, parenthesis bracket and curly braces, determine whether it is valid. Every opening bracket must be one simple. A lot of this stuff today just happening here. So given a string of brackets containing the character, parenthesis, say brackets or curly braces, determine whether it is the condition for valid. Every opening bracket must be closed by a matching bracket of same time. It means that if we get this bracket, there should be a bracket of this closing one. If I got a bracket like this, there should be someone in the future like this. And if some curly braces, in future we need something in curly braces. Maybe inside this there is another brackets, but same time, opening, closing of same time, opening and closing of same type of closing and opening we should get here. Okay, this is a valid one, and obviously this is not a valid one. It's not a valid one because inside these two brackets there is a closing bracket, not any opening bracket. This is not a valid one, but this is a valid one. This is a valid one. A valid one. It is a valid one because every has a closing. Every opening has a closing. Every opening has a closing. This opening has this closing, but what about this? This has nothing. Nothing. This opening doesn't have any closing bracket. This closing bracket doesn't have any opening bracket. So we have to make sure that every opening bracket should have a closing bracket of the same type. Of the same type, not any different. Although this is not a valid one. This is not a valid one. So the brute force approach is a very simple one. Also, I don't write the code for this. So we just check every matching pair of bracket. We use two loops for this. We can easily use two loops and store everything inside it. And every time we got it, we delete it. And at the end, we just take that if our string is empty or not. Okay. The string melted away valid. So at the end, we check that whenever we delete, after deleting everything, is there anything left on the not? If there is nothing left, we just return true. But the optimized and the most efficient approach is this stack one. So what is our approach? Uh, let's take a stack. Take a stack, okay? And this is our bracket. This is our brackets. This is our brackets. All of the brackets are this. So first, in the stack, we only store the opening bracket. And what are the opening bracket? These three. In the stack, we only store these three elements. Okay. So just go there. Is it a opening bracket? Yes. Add it. Is it a opening bracket? Yes. Add it. Next one. Is it a opening bracket? Yes. Add it. Next step. Is it a opening bracket? No. Is it a closing bracket? Yes. Is if this closing one and this top element, the top element is the opening of the closing bracket. So this bracket is closing and this bracket is opening. Is it true? Yes. So for that reason, just simply remove it from the stack. Okay. Now move to the next element, which is this one. So for this bracket, this is the closing bracket. This is not an opening bracket. So for this bracket, does the top element of the stack is the opening bracket of this one? Yes. This is the opening bracket. This is the closing bracket. Yes. It's matching. So just remove the element from the stack. Now go to the last element. This is our last element. So is it a opening bracket? No. Is it a closing bracket? Yes. Is the stack top is the opening bracket of this closing bracket? Yes. 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 So just remove it from the stack. And now we completely traverse the whole array. And is there anything left in the stack? No. Suppose here is also opening bracket. So we can easily store opening bracket. Another closing bracket. We just check, okay, opening and closing match, just remove it. The stack is empty. But suppose we have a opening bracket here. Okay. So we insert it. But in the next step, there is nothing. The string ends here. So when the string ends here, is the stack is empty? No. It means it is not a valid one. This string is not a valid one. Or if we had anything like a closing bracket one. So we just check, this is the opening bracket? No. Is it a closing bracket? Yes. So does the stack top is now assigned to this closing one? No, because stack is empty. So the top is also empty. So the closing bracket is not associated with the top. So we just simply remove false here. So every time we have to ensure we only insert value of the opening bracket of these three. We only insert these three value, and when a closing bracket come, we just check if the top element is the closing one or not. If the top element is the opening bracket of the closing one or not. Okay. So this is our solution. Let's visualize it. Most recent open closes first. It is always the rule. Which is the most recent open is always the first one to close. And with this help and the LIFO property of stack, we just implement it. So first, stack is empty, push it. It is an open bracket. So for every open bracket, we just have to push the element to the array, to the stack. Next is also opening one, so push the element to the stack. Next is also opening one, so push the element into the stack. And now we got a closing bracket. The stack is not empty. Okay, the stack is not empty and it requires a opening bracket of the curly one. It matches. Then simply remove the one from the stack and go next one. This is a closing one and this is the matching opening one. Matching, same opening one. Just remove it. This is the closing one. This is the matching opening one. So just remove it. And then just check if the stack is written or empty or not. If it's empty, we can easily say valid. Okay. So now just write the pseudocode. Function. Inside we can take an s, which is nothing but a string. So take a stack, which is nothing but an empty stack, an empty stack. And now for each character in s, so for each character in the string s, we have to check that if character is open, if the character is opens, then simply push the character. If the character is open, then simply push the character. And otherwise every time check one thing, that if anytime stack is empty and we have a closing one, stack is empty and we have a closing one, we just have to return false, because we don't check anything. If stack is empty and or stack is empty, in any cases we have an element which is in bracket and the stack is empty, we reach a bracket which is closing, which is not fit into the if statement, and we check the stack is empty, it simply means we don't have any opening bracket and we get a closing bracket, so it's not a valid string, so you have to return false here. Or the top is mismatch. uh, suppose in the stack suppose in the stack we have this one, but we get a closing bracket of this one, so these two doesn't match, so this opening bracket and this closing bracket doesn't match, so return false for this. Top mismatch, top mismatch, then simply for this case return false. And now if if we have if the stack is not empty and the top is not mismatch, so in this case simply pop the element from the stack and at the end return st.empty. If the stack is empty, then it's good to have, otherwise it is a false or not a valid string. So yes, we nailed it. So this is our pseudocode. Let's write down the actual code here. Okay, so first we need a stack, and first like take the size of the string. First we take the size, then the stack, take a stack which is nothing but int type, which is st, let's take it as st. And now for every character, for every character in s, check one thing, that if the character is open or not. And how could we check? If the ch is open or not. So if the character is equal to this one, or the character is equal to okay sorry this open bracket, or the character is equal to this open bracket. So we got three open bracket. If the character matches with any of the three, just push it to the stack. So st.push the character, just simply push it. And if it not into opening bracket, it means it is, or the character is a the character is a closing one. And before check anything, check if uh, let's write the some comments here. So if stack is empty, then return false. If the stack is empty and we encounter a character which is a closing bracket, then simply it means we don't have any opening bracket, so we can remove return false here. Otherwise we have to first check the top element, check the top element and answer it. So first, if it is a closing one, and first we have to check if the stack is empty. If the stack is empty, then simply return false. Now so character, let's take is a stem or top element more. So we take the top element from the stack, which is st.top. Okay, so now we get the top element. And now we have to check the value is mismatch or not, this condition, and if the top value mismatch or not. Okay, so if any time the top value mismatch, we have to just return false. Okay, otherwise we have to pop it. So first check when to pop. So if value matches, then pop element from the stack. Okay, so how could we say the value is matching? Value can be matched in three conditions. That if the character is equal to the opening one, sorry, the character is actually the closing one, and the top element is the opening one. Lot of this stuff today. So if the character is the closing one, and the top element is the opening one. Okay, or if the character is the closing one and top element is the opening one. So if these three things occur, any of these three occurs, then simply say st dot pop. So just pop the top element from the stack. Just pop the top element from the stack. If current character is a closing bracket and the top element which is at top is a opening bracket, it means it is a perfect match. It is a perfect match. It is a perfect match. So the current element is this and the stack top is this. This is a perfect match. We have to ensure it. Same with this bracket, same with this bracket. As simple as that. And at the end, just ChaiCode. Just return one thing. Return st.pop. st.empty. So if the stack is empty, it returns true. If the stack is not empty, it returns false. So let's run it. It's working. Let's submit it. Okay, it gives us an output. We make some mistakes. Let's check it. So we push the element. Okay, any of the three we push the element. It's a closing one. If the stack is empty, then simply return false because we can't get. Otherwise take the top element, and check if this condition works. So it should work. So just we push this element. When you go and check, and we have to make sure that here it's not possible, then simply return false. So if any of these three cases doesn't work, we have to return false. We are missing one condition, that if any of this condition doesn't get, in else case we just return false. As simple as that. So this is our solution. Here we are just using one stack, but also at the end the stack should become empty, and we are using one for loop to traverse the whole string. So it is big O of n is the size of the string. Also you don't need this n here actually. The time complexity is big of n and space is big of n. As simple as that. So the time complexity will become big O of n, and the space complexity will become O of n because of the stack. Because of the stack. So this is our question, valid parenthesis. Thank you very much. Go link to get a 7-day free trial. Use this platform. Thank you.